Cool, thank you. I guess I should lift this up a little bit. Yeah, so my name's Dino Dai Zovi. I'm I call a fun employed security researcher right now, or a professional gentleman of leisure with a side interest in security research. All right, so yeah, follow me on Twitter. Actually, does anyone follow me on Twitter? Wow, this is like almost most of the room. All right. It's kind of weird because I feel like Twitter's this alternate universe, and then wherever it intersects with the real world is always very strange. All right. Why are we not advancing? All right. Okay, so what am I going to talk about today? Why am I here? I'm going to show what I call the practical applications of return-oriented programming, which is basically return-oriented exploitation. Return-oriented programming was introduced as an academic paper, kind of with a lot of bells and whistles that are not necessarily needed for exploitation, and I'm going to kind of cut away a lot of that cruft, distill it down to what's actually useful so that we can write reliable depth evasion and NX evasion exploits using these type of techniques. And the point that I'm going to make continually is, for the defense side, preventing the introduction of malicious code is not enough to prevent the execution of malicious computations. And I ripped that off completely from the original paper because I think it's a very great point. And anyone looking at defense systems, whether they be operating system mitigations or security products, they all so often rely on these simple tactics, like attacker tactics that they try and stop. Like one of them is introducing malicious code, which is only the most flexible way to exploit a memory corruption vulnerability. And so we need to kind of expand the box and think a little outside the box. And I'm also going to demonstrate that while exploitation mitigations make exploitation of many types of vulnerabilities more difficult, they haven't stopped it. And they do not prevent all exploitation. So we need to kind of keep that in mind. Every system has its failure points. Also, get on my soapbox about sandboxing and other things about how the multi-user operating system is largely a bad fit for the single-user desktop because you're the only one using it. But what you want is a application isolation security system like you have on your mobile phone. You want that for the desktop, not multiple users, because you really just want you and privileged operations. All right, so what I'm going to talk about today, talk about a little review of current state of exploitation, talk about the new return-oriented exploitation, and I talk about how to apply this to bypassing permanent depth, give a in-depth demonstration or an explanation of how the IE Aurora, the Operation Aurora vulnerability, how that works, how it was caused, and how we may exploit it. And then I'm going to demo my exploit for IE8 on Windows 7 using this technique, which uses return-oriented exploitation to bypass permanent depth. And then I'm going to go a little over my toolkit that I wrote for myself to do this, what I call BISC, which stands for the Borrowed Instruction Synthetic Computer. And then I'll draw some conclusions and stuff. So let's start with a review of where exploitation is these days. So the way I look at the history of memory corruption and exploitation is someone points out an exploitable case. And then the defense says, oh, we can fix that. And then there's another exploitable case, and they can fix that. And basically, we just keep kind of doing this song and dance and never really kind of backing up and saying, okay, software is soft. You can make it misbehave, and you can get bad things to happen. We need to defend it a little farther back. So the Morris worm basically did the same cookie cutter style stack exploit, or stack buffer overflow and payload that was in Aleph 1 smashing the stack. Basically identical. And it was like a technique lost for 7 years till Thomas Lopatic rediscovered it. And then, it was, once it got in FRAC, a lot of people were aware of it. And then everyone looked for all stack overflows. And you have a lot of people saying, well, this is the only thing that's exploitable. We don't need to worry about it. And then Solar Designer dropped some space alien technology on how to exploit heap buffer overflows by overriding the linked list pointers in heap free blocks. So now we're like, oh crap, heap overflows are exploitable. We got to make sure we catch all those. And then integer overflows. And there's a whole ton of surprise, surprise, in a non-type safe language like C and C++, there's a whole lot of unsafe conditions. And we keep kind of running into the same things. Some of the better approaches to this are exploit mitigations. Say, all right, well, we're working on finding all the vulnerabilities, but we won't find them all. And so we may as well try and make it difficult for the exploit developer to get a meaningful exploit, because vulnerabilities don't own people. Exploits own people. So if you can stop the exploits, you're actually making progress. And starting with XP Service Pack 2, mainstream operating systems started shipping with exploit mitigations. This included protected stack, protected heap, things like safe SCH, and both software and hardware enforced data execution prevention. This is a big step forward. I think the biggest step forward was the introduction of ASLR with Vista, which, to give credit where it's due, it was invented and first implemented in the PAX project for Linux. And what all this stuff does is this makes exploitation more difficult, and they're sort of additive. As you keep adding on, it's really hard to read. As you keep adding on more mitigations, your exploit difficulty, the time to take a vulnerability to an exploit, or even the probability that a vulnerability can, or the number of vulnerabilities that can be turned into reliable exploits, shrinks. And for those, the time to develop a reliable exploit grows. And what this also does is these mitigations eliminate entire classes of exploitation techniques. So the protected stack, for instance, completely killed the stack return adjust overwrite. The vanilla stack overflow, if you compile with /gs, for the most part, it's gone. So then attackers had the SEH frame overwrite. And then basically you had other mitigations for that. And this is kind of how exploitation has moved forward. And where we are now is we're basically in the heap-free blocks. We have protected heaps now. Those are kind of out of fashion. And so what you're looking for is application-specific data, in particular C++ vtables or any other function pointers. And after those get protected, well, you have to figure something else out. And these mitigations, you always have to keep in mind that some come for free with the operating system, some require compiler, upgrading to a new compiler, and some require the application to opt in. So you won't, even if the operating system supports all these, like you have an application on Windows 7, you may not have all these. It depends on the OS vendor, on the compiler that the application uses. If they use the Intel compiler instead of the Microsoft compiler, they won't have the same mitigations. And it also requires them to opt in to certain mitigations like DEP and ASLR to kind of declare that their application is compatible with it. And these are additive. So basically you can get 2 of the 3, but they're real sweet spots in the center when everyone's playing together nicely and you have the most secure app possible. But what's difficult for the end user or for organizations looking at the security of their desktops is it's very difficult to find out exactly which mitigations are 1, active, and B, 2, effective in this process. Sometimes the application may say it has one of these mitigations, but for one reason or another, they may actually not do anything. And for instance, like things like safe SCH, if one module can be loaded that does not opt into safe SCH, that'll allow exploitation, and it'll basically destroy the security of the entire process. So this is actually very complex. And so if you look at your web browser, it's really hard to know how secure is this? Microsoft gives you a performance rating for your operating system or for your hardware. It'd be nice if basically for your browser configuration, it could say, yeah, you're running at about a 4 right now. And if you install something like, I'm not going to name a vendor's name or a plugin, all of a sudden you drop down to a 3 and they're like, yo, you just dropped your security down to a 3. I hope that game that you wanted to play was worth it. And so while the operating system out of the box may be pretty solid, once you install any third-party software, the security posture of your browser or another application may be weakened. So just keep in mind, I'm going a little quickly because I have like 70 slides, so I wanted to cover a lot here. So let's talk about return-oriented exploitation, which is what I call the new hotness. Started out with return to libc. This is, again, like most good things in computer security, with space alien technology delivered to us humans by Solar Designer by way of bug track. This is basically attack was recognizing, well, this is an evasion of the first exploit mitigations, which were non-executable stack segments. And so the idea was, well, we're overwriting the return address. Instead of jumping into our shell code, we can jump into existing code. This was code reuse. And so, for instance, instead of executing shellcode, why don't we return into the libc library and return to the function system? So if you're not a programmer, the function system will execute a string using the command shell. So if you call system and binsh, it'll give you the shell. So instead of returning to shellcode, just return to system with a pointer to binsh from somewhere else in memory. Boom, you have a shell. So your non-executable stack doesn't do anything. And if that's not enough to do it, to get to achieve your goals, you can do its return chaining. And this exploits the fact that on x86, your return address and your arguments all come from the same stack. So if you've obliterated the stack and control the whole thing, you control not just the control flow, but also the arguments. And so what you're doing is you're returning to a location of memory, which is like the top of the function. And in essence, you're simulating a call to that function. Because when it accesses its arguments, it's going to read data that you control from the stack that you've overwritten. And you can chain these together so that you can call one function, another function, another function. The big difficulty here, though, is using the return value from those functions. It's not exactly like C code. You have to kind of do a couple things. But you can only do like a few hops, and you have to do some tricks to pass values from one function to the other. But it's enough to have significant damage. Let's kind of go through quickly kind of how this works with some nice pictures. I tried to put as many pictures as possible in this presentation because I did a similar thing for RSA, and I had I think a third of my slides had pictures, and they still said not enough pictures. So I hope the pictures aren't overwhelming. So on the left here, I'm going to kind of show the assembly instructions that are getting executed. And on the right, I'm going to show basically how the stack is unwound and highlight in yellow the value that is being read. So first, we've overwritten the stack. We have a stack overflow, and we're executing the return instruction, which is going to use a value that we have chosen. And that's going to jump elsewhere in memory. And that's going to jump to the top of a function. And so it's going to save the EBP, save the frame pointer, and overwrite the existing return address. And importantly, later on in the function, it's going to access an argument. And it's going to come from the stack that we control, argument 1. And then it's going to reuse the saved frame pointer. And then it's going to return using another return address that we control. And this is going to be the address of a pop-pop-ret sequence, which will basically just advance past our arguments on the stack and then return to the next return address that we use. So basically, the pop-pop-ret pops off the arguments into registers because we don't really care what happens. We just want to skip past them, and then executes a return instruction using the address of the next function we want to execute. So that is how we use return chaining to chain returns to two different functions when we control the entire stack. So return to libc and return chaining are kind of the primordial ooze from which ROP was born. And this is enough to evade a good number of protections. Most notably, Scape and Skywing documented this technique to call NT-set information process, which would just disable dep for the entire process. So dep would be on, you just return there, turns off dep instantly, and then you return it to your shellcode. So done. And basically using return chaining is enough to do that. Also, this is enough to use the write process memory technique, which is, if you're on full disclosure, it was kind of interesting. Basically, it uses write process memory to patch the function itself so that it writes into its own code and then it starts executing from there. So it's a cool one-hop dep bypass technique. So after these kind of things, basically Microsoft had to react, and they reacted with permanent dep. So once dep is turned on, you can no longer just turn it off. Of course, if your application uses this feature. So if you're running IE8 on Vista SP1 and above, it'll use permanent dep. Otherwise, it won't. Or no, on Service Pack IE8 on Service Pack 3 and above, or Service Pack 3 will also use permanent dep. Otherwise, it won't. So again, it's this mismatch of supported configurations and a matrix on what mitigations you actually have and what actually work. So after permanent dep disabled some of these easy techniques, which the write process memory also gets past permanent dep, but it required attackers to up their game. And the response to this is return-oriented programming. And the kernel of the idea here is that instead of returning to functions or sequences of instructions, you return to arbitrary bytes that may or may not be the intended instruction, and you return midstream. So here in the, wow, it's a different color on there. You can see basically in the picture here, see, imagine you have the instruction move EAX on a 32-bit constant. That gets encoded into those 5 bytes that I show there. But if you return 1 byte in and only decode the last 4 bytes, it becomes the instruction sequence move EAX into ECX plus 8 and then return. So this is the main idea of ROP. Basically, you can find these instruction plus ret sequences anywhere in memory, and you can build them, combine them into something else. Or the best way to understand it, to credit Dr. Raid's girlfriend who thought of this, and we all think she's a genius because of it, is that it's like a ransom note. Return-oriented programming is like a ransom note, but instead of cutting out letters from magazines, you are cutting out instructions from text segments. which is basically exactly what it is. You're taking little bits, putting them together to have a higher order message. Build them into words and build that into the note. And in the terminology return-oriented programming, these are called gadgets. You take kind of these useful sequences and combine them to a gadget. And a gadget is a high-level operation that is somewhat useful. So a gadget could be something like writing a chosen value to a chosen location. It could be modifying a value in memory, like adding or subtracting, logical operations, and so on, or calling a function in a shared library. So as an example, here's the simple gadget to do a write value to memory. If you have these three sequences, a pop EAX ret that sets EAX to a value of your choosing because it's reading all of this stuff from the stack that you control. You have a pop ECX ret, loads another register with the value you control, and then to the instruction move EAX into ECX ret. Basically, you can combine these three operations, and you have the gadget to write the value you choose to a location you choose. And just to kind of show how this works, we'll use my little stack diagram again. So we're starting out executing this code at the top that basically we jump to because we have control of the, of the stack. And then it's going to do a pop EAX, which is going to load dead beef, a value that we chose, into EAX. Now it's going to return again to the next location in memory of a useful sequence, which will execute a pop ECX, load feed face into ECX, and then it'll return to the third part of the gadget, which will move dead beef into feed face. So this is how you feed your face dead beef in return-oriented programming. And then it returns, which is not on the stack. And so it goes on to do something else. So you take these gadgets and you build what's called a return-oriented program. And you do this by scanning all of available memory for useful instruction sequences, and you kind of combine them into the gadgets. And then if you found enough gadgets to kind of form what Havav Shakam calls a gadget catalog, these are the kind of the core operations you need to have a Turing-complete language, you're done. And basically, you can actually use this as the backend for a C compiler. So in his initial paper, they actually wrote a compiler for this. So they compiled QSort to use only return sequences into libc. And it took like 1,000, 1,500 bytes, but it demonstrated that it was Turing complete, which is their big work. Again, what this shows is preventing the introduction of malicious code is not enough to prevent the introduction of malicious computations, because these random bytes in memory can be composed to achieve whatever the attacker wants. So what does the attacker want? To bypass DEP. So kind of give you a review of what DEP is. Hardware-enforced DEP uses the NX or XD bit of x86 processors to enforce the non-executable of memory. So on x86 processors, on the original ones, you could set the permissions. Like the operating system will tell you that a memory page has a readable, writable, and executable permission. And so most pages will be readable and executable, or will be just readable and writable. But if it's readable, it's also executable. And so what I call the NX and XD bits, I call it the I really mean it bit. Because if you don't set the I really mean it bit, being readable will mean executable. And that's even on newer processors. So you have to be in PAE mode and then set the I really mean it bit for the processor to do what you expect. And then, if that wasn't enough complication, that means that applications and operating systems may not get it right. It requires every application to be compiled with the NX compat flag. Otherwise, DEP will get disabled. Or it can turn it off dynamically, blah, 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 blah. So permanent DEP allows the application, like Internet Explorer, to say, DEP is on, I don't care what any ActiveX control says or does, or exploit says or does, don't turn it off. And so to get around this, we're going to use return-oriented exploitation. So I call these return-oriented exploits, which basically involves 3 steps. The first step is what I call the stack pivot, because the most important thing to control is the stack pointer. And like I kind of phrase this as ESP is the new EIP. Just getting EIP is not going to buy you much with DEP on, because you can't execute memory. So what you have to do is use control of EIP to get control of ESP, which you can then use to get control of EIP again. But the stack pivot step basically points the stack pointer into data that you control. And there's a variety of ways to do that. You find a sequence that will move a register that points to your data into ESP, or will adjust the stack pointer, add or subtract enough to point the stack pointer into something that you control. So if you control a string buffer farther up the stack, you can pre-populate that with your return-oriented program, and then point the stack pointer into it, good to go. And so this attacker-controlled data can contain a return-oriented program, which can either be a fully return-oriented payload that uses all return-oriented program to do everything, or it's easier is to just make a return-oriented payload stage that just uses ROP to basically evade DEP and then execute a traditional payload. And so that's basically what I do. And there's a variety of ways to do this, because DEP does not mean that the application can't allocate more executable memory. So you can just allocate executable memory, copy your payload into it, and execute it from there. Or you can make, what I like doing is I like doing the virtual protect ESP. I just make the stack executable again. And it's like, because this is less code. Just make it executable, go right there. So, it works. So if you have a stack pivot, return-oriented payload stage, which is reusable, and a normal payload, you can get it at your local convenience store or Metasploit, wherever you want, you have a permanent DEP bypass exploit, and you're basically done. So what this means is that DEP without ASLR is weak sauce. It's really like, it just makes the attackers work a little bit, but even by the time permanent DEP came out, it had already been published how to evade it. Just to give you an idea of how old this stuff is, like the original return-oriented payload, return-oriented programming paper, I think came out in 2007. And a lot of this return-oriented programming, return-oriented exploitation stuff has been talked about since 1997. Nothing I'm saying today is anything new at all. Everything I talk about is at least 2 years old. It's just hasn't really been put into practice. So basically, ASLR kind of comes in degrees. If you have no ASLR, it's really easy to turn off DEP because you have a bunch of material you can use for return-oriented programming. If one or more modules do not opt into ASLR, basically you just confine your search to that module. So if you know that module A is at location X, you just scan that and build your entire return-oriented program based on that. If everything opts into ASLR, then it's a little more difficult because you're not going to know where anything is, and you're going to need to use memory address disclosure vulnerabilities or some other tricks to kind of figure out where things are and build your return-oriented payload. This was done by, I'm going to massacre his last name, I'll just say Peter at Pwn to Own this year at CanSec West. Sorry? Rubdenhill. Yes, he had a technique to not terminate a Unicode string, I believe, and so he could read the string, and that would basically give him the V-table from an adjacent object. Once he had that, he could build. He said, "Oh, with this V-table, I know it's MS-HTML or whatever. I know that MS-HTML is at this address, and I can build my return-oriented payload based on that information." So even with full ASLR, not all that secure, or there's still ways around it. It is secure, but it just makes you have to find another vulnerability-like thing. So you have to combine a memory corruption vulnerability with a memory disclosure vulnerability, and then you can actually make use of the corruption vulnerability. So let's talk about putting this into practice to exploit the vulnerability that was exploited in the wild in the Operation Aurora attacks. So, so here's basically the crux of the issue. There's an event param object that this is a C++ object, in MS-HTML. And when in JavaScript calls create event object with an existing JavaScript event, this event param constructor doesn't increment the reference counts for pointers that it uses. So it has a pointer called source element, and it just copies the pointer value. And source element is a pointer to the C tree node, and it copies the pointer without incrementing the reference count. This is bad. As you go, you have the event param pointing to a C tree node and the C element, which is the representation of the HTML element that fired the event, both pointing to the same memory, but only one of them has a reference count. And that's why the C element has the strong arrow and the source element under the event param has the weak arrow. It points to that memory, but because it's not reference counted, it doesn't strongly point to that memory. If, for instance, you remove the original element from the DOM tree, it'll free that memory and decrement the reference count to the C tree node object. If the C tree node object reference count is 0, which is the normal case because it only had the element pointing to the C tree node, the object will be freed. When it gets called to the destructor, it'll say, my reference count is 0, time to free myself. So what that means is you have a use after free situation. An attacker can cause controlled allocations of the right size to replace that object in the heap with an object that they fully control. So they have created their own C tree node with fully controlled data that event param points to. And then if you do a virtual, do some calls on that event param and it gets used, it'll basically jump through memory that you control. It'll do a C++ virtual call using a vtable pointer that you chose. And so how we exploit this is our crafted heap block will have a pointer to a fake C element, and this fake C element is actually where the vtable is. And so C element has a pointer to a forged vtable. And so what an attacker can do is attacker can build all of this in their heap spray. So they can heap spray the heap with a kind of self-referential data structure that it just has to satisfy these properties so that the app, when Internet Explorer is using it, as the code is written, it'll behave how the attacker wants it to behave. And this vtable will have pointers to other code so that when the virtual function call through that vtable happens, it will use a pointer value that the attacker chose and do a stack pivot using an exchange EAX ESP instruction, which will point the stack pointer into the heap spray that the attacker created, which will have what I call people either call a ret sled or I like calling them ROP nops. And basically they're the address of a return instruction, which basically causes the stack pointer to kind of increment until it hits the return-oriented payload stage. And from the return-oriented payload stage, allocates memory, blah, 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 blah. So let's see what that looks like. All right, come on. Okay. All right, I sacrificed my goats to the demo gods last night, so let's see what happens. So this is Internet Explorer 8 on Windows Vista 7. It is obviously unpatched for this vulnerability because if I did that, the demo would be very short and very boring. So I just have like a little run exploit button that calls my JavaScript to actually do the full exploit. And we do that, and oh, how'd that happen? Got a calculator. Oops. Oh, crap. I wanted to do some arithmetic. Hit it again. Oh, okay, there we go. So, boom. That's all it takes. And well, I already hit it twice. Let's hit it again. So everything's moving onto the web. That's one of the things that security people complain about. And pretty soon, you won't actually have a desktop calculator application. And so you'll need to go to an exploit web page to actually launch a calculator for you. Exactly. So that's basically how it works. So let's talk about, next slide. Come on, there we go. So give you a little details on my implementation of this that I call BISC, just because it rhymes with RISC and CISC, and I thought it was clever. And I like saying like iPhone BISC or Windows BISC. It's like a lobster bisque, kind of tasty. Which stands for a Borrowed Instructions Synthetic Computer, which is kind of a backronym. I thought of the name before I found out what it stood for. And that's actually version 2 of what it stands for. I think I like it better. So basically what BISC is BISC is a small Ruby library for demonstrating how to build borrowed instruction programs. Notice I now say borrowed instructions, not return-oriented programs, because return-oriented programming must be Turing complete, according to Hovavchikam, the author of it. So I don't support branches or conditionals. So I'm going to call these a borrowed instruction program. Because for evading dep and stuff like that, we don't actually need conditionals. We don't need loops. Who cares? But I want my exploit to work. So the design ideas are, 1, keep it simple so it works, and try and make it easy to use. And so to do that, I made it analogous to a traditional assembler. Like you write your return or your borrowed instruction program in real x86 assembly. And the assembler kind of just translates that into return addresses of those instructions so that it basically does what you write. And also try to minimize the amount of magic behind the scenes and also allow users to write macros to make their life a little easier. So here's kind of a compare-contrast of ROP versus BISC. They both reuse single instructions followed by a return. ROP composes instruction sequences into gadgets. BISC doesn't. You have to write your code in individual instructions. ROP is Turing complete. BISC isn't. BISC is opportunistic based on the instructions available. So depending on the target, you may have to do things a little differently because an instruction that you're using may no longer be available. It's definitely not Turing complete because it's a whole lot of work. And ROP you can compile to from a high-level language. BISC, the highest level thing you can do is write macros, but makes it workable. And so to keep it simple, we don't need a full compiler, just an assembler, and that's basically all I wrote. Because for the exploit developer, x86 assembly is not scary, and it shouldn't be. If you find x86 assembly scary, perhaps you shouldn't be writing exploits because that's what it takes. And we only need to support a subset of x86. We don't need to support all the esoteric instructions. We only need kind of the core, some core, like even 12 instructions that we can use. And so we can write programs using a familiar syntax, and the assembler will scan the libraries you give it to just try and make it happen. Again, no support for conditionals or loops. So here's kind of if you can read this, an example of a small scanner that you give it a DLL, and it'll print out the available instructions that you can use for your BISC programs. Some ones I want to point out, this one right here, move EAX, ECX, that we can use that to read memory. Oh, sorry, first I should point out, you see all the pops over here? Those let us set registers to arbitrary values. Very important. You need at least a few of those, otherwise you're not going to get anywhere. If we have a move ECX into EAX, that's our memory read. We can set ECX, we can read from ECX, we can now read memory. We also have plenty of writes and a couple other useful things. So basically that's enough to write useful BISC programs. Now to wrap your head around how this works is the programming model kind of takes a little bit to get used to, because when you think about very literally how the stack works, the stack grows downward but unwinds upward. And we're going to write our return-oriented, borrowed instruction programs downward. So it kind of flipped. Basically, you can see in the picture in our code on the right, there's ret 1, 2, 3, 4, but those are upside down on the left because they're being unwound in that order. And so each identified instruction is a word in your vocabulary. So while having a larger vocabulary makes it easier to get your point across in a more concise and more precise way, it's not necessary to communicate. So basically, if you look at how this works, you have to work with the instruction, the vocabulary that you have to get the point across. Like on the right, it'd be nice to be able to just add 3 to the memory pointed to by ECX. But you probably won't find that instruction. So you just need to execute the 5 instructions on the left, which will perform the equivalent operation. So it does take a little problem solving and creativity. Here's how my BISC programs look. They're an array of strings and values. A string is an instruction that gets replaced with the location in memory of that instruction, and a value is a literal that gets put right into the stack. And you can also make your arrays nested. So basically, what'll happen is it'll flatten the array and then it'll interpret it. So that allows you to write macros, because you can write a small function in Ruby that'll return just an array. And so you can kind of compose these, you can nest these, so it can be an arbitrarily nested array, which lets you have macros that use other macros, and so on. So here's a kind of a quick example of what a small program looks like. I have the macro called clear, which again uses some creative kind of backflips to clear. You give it a pointer and it clears that value that's pointed to by doing some crazy stuff, by setting it, by ORing it with FFFFF and then adding 1 to it, because well those are the pieces that we had, so I had to do you need to use what you have to achieve your goals. And basically the main code is just this function main down here, which just calls clear on a variable that was allocated. There's an allocate function that will allocate you some dedicated memory so you can use for variable storage. And that's basically, I just run this and that'll spit out, like I run it with a list of a DLL, and it will generate this BISC program for that DLL. So assuming that DLL is loaded in memory at a fixed location, or I can say, load it, generate it with this DLL at this specific location. So if I have a memory address disclosure, I can then just rerun this and generate it for that runtime configuration. So you can also, because you have to do these kind of backflips to achieve these simple operations, and if you use a different DLL to target, all those same instructions may not be available. The idea of the Bisq macros is that you can treat them as virtual methods. So you can basically write your clear function, your set function, and so on, so that you basically write your payloads in terms of those macros, and then when you target a different DLL, you basically just need to re-implement your macros instead of re-implementing your payload, which is much easier. And sorry, Bisq is not available. There already is, sorry, yes? You're free to do whatever you want. I'm presenting here, so my personal opinion is I think releasing code like this would only help malware, so I personally don't want to do it. For people who do want to try their hand at this, Alex Soderov and I give a training called Assured Exploitation. We did it at CanSec West this year. We'll probably do it at CanSec West next year, where we give students a individual license for this software, and then we teach people how to play with it, and they can write their own exploits with it. Wow, I really went very fast. So return-oriented programming can be applied in other fields. Most notably, where you need it is the iPhone. So the iPhone has a code signing enforcement policy, which is basically the biggest security strength of the platform, meaning that you can't inject new code. If you try and jump into, they have NX, so you can't jump into the heap where you've injected your shellcode. You can try and jump into mprotect and make new memory executable, but the kernel will deny it because that memory has not been signed. You can try and change memory, change code that's already loaded, but if you make it writable, then change it, and then try and make it executable again, the kernel will deny it because you have set the dirty bit and the signature has been invalidated. It won't let it happen. One thing to keep in mind, the reason most people don't talk about this is because they do all their testing on jailbroken phones, and the first thing jailbreaking does is it disables code signing. So that's how you can run unauthorized apps, because the code signing enforcement means that the only code that will be executed by the processor on your iPhone is code that has been signed by Apple and blessed in some weird, pagan ceremony with Steve Jobs present in holy robes. And that's largely a security strength of the platform. And so also be aware that if you're jailbreaking your phone, you are making it 1,000 times easier for an exploit to work on that phone. So, I hope that game was worth it. For instance, at Pwn to Own this year at CanSec West, Ralph Philippe Weinman and Vincenzo Iozzo, who unfortunately couldn't make it here because of the crazy ash cloud, they demonstrated, they won the Pwn to Own for the iPhone with a fully return-oriented payload. So basically, it wasn't a payload stage like I've demonstrated. It used fully return-oriented programming to read the SMS database and send it over the network, which I guess I wouldn't think that the SMS database should be available to all applications, but it's allowed by the sandbox. So they didn't actually have to go and break out of the sandbox to win. Another useful application of return-oriented exploitation is on embedded systems. Embedded systems very often have separate instruction and data caches, and this causes a lot of headaches for exploitation, because if you're trying to inject new code, that's going to be data, and that's going to be in the data cache. And so if you try and point the processor at those memory locations, it's going to get the memory, it's trying to execute code directly from memory or from the instruction cache, which it'll be desynchronized. It won't have the same information as in the data cache. So you'll find this on PowerPC, you'll find this on ARM. I can't remember if MIPS, I don't think MIPS has it. So that's another useful place. The way that I do these techniques is actually most similar to Sebastian Kramer's borrowed code chunks technique. This was like a draft paper that he kind of put on the web that didn't really receive anywhere near the amount of attention that it should have. And this, this predates return-oriented programming, the academic paper. And this is the first place that I can find that had the key idea of looking for a single instruction and then a ret, a return instruction, and then building higher level things out of that. So that's kind of a monument. That's like a big milestone in the development of return-oriented exploitation. Most recently, another academic paper showed that these techniques could be leveraged against secure hardware platforms, where, for instance, they might only have code loaded in ROM and not actually execute code out of RAM. Well, if you use return-oriented programming techniques, you can still execute whatever you want using just fragments from that already loaded ROM. So in conclusion, return-oriented techniques are increasingly necessary for exploiting vulnerabilities in the face of NX, DEP, and other modern data protections and exploitation mitigations. Bypassing something like permanent DEP does not require a fully return-oriented payload. It just requires a return-oriented payload stage, which is just a bridge to actually execute your code. ASLR is kind of a very, with return-oriented techniques, ASLR is very much an all-or-nothing mitigation, because if there's one module that does not opt into ASLR, you can use that to execute your full payload. And also, ASLR of data is not as thorough as you'd think. For instance, heap sprays still work because the only bits that are randomized, like the beginning of the heap is randomized by something like 1 megabyte. But if you're allocating 100 megabytes for a heap spray, whether your data is like here or here, doesn't really matter. This is not a lot of wiggle room. So you still have a lot of opportunities for exploitation there. But in a secure application, like secure process that has permanent DEP, full ASLR, that significantly raises the amount of work an exploit developer must perform, because they need a second vulnerability. They need a memory address disclosure vulnerability to enable the exploitation of the memory corruption vulnerability. And yeah, the iPhone is tough. Again, we need to stop thinking of the introduction of malicious code as being the big thing to defend against. So how do you apply these sort of conclusions to your world? If you are IT security for an organization, you need to be aware that malware may eventually use these techniques to exploit DEP-enabled processes. Actually, I need to update this because I think a week after I gave my RSA presentation, there was a Adobe Reader exploit that actually used return-oriented programming to bypass permanent DEP. So they were obviously in my RSA presentation and put that into practice really quickly, which I apologize for. I didn't know that that would happen. Being sarcastic. Cat's out of the bag. But it was one of those things where it was really I think, more to the second point, malware analysts need to be prepared to look for things like this, because I think this sample that they found kind of snuck through because it didn't look like normal exploits. You didn't have a lot of the same indicators, and you just had a big string of memory addresses. You don't see I didn't even know it was there when I first looked at it. I was just like, what's this huge blob? Where's the payload? Yeah, exactly. Like you said, you see a big blob of binary data, but where's the payload? And imagine tracing through it. You can't throw a return-oriented blob into IDA, and it may be dependent on where a module is loaded at by ASLR at runtime. It means the tools we have for analysis are just not adequate to analyze this. So it requires for malware analysts, you need to develop something that will basically deserialize this ROP payload and the address space. You may need some. Yeah, you might need a complete memory snapshot, as you pointed out, and then something to kind of interpret and deserialize that ROP payload to something that you can read and analyze the effects. Yeah, or runtime tracing will definitely see it, because you'll see what actually what actually is performed. But it's something that may be subtle. We need to keep our eyes out for this. For software vendors and people who work, developing products, you need to remember that DEP and ASLR help. They're the safety net. but they don't make your vulnerabilities, non-exploitable. They will make a lot of them non-exploitable. They'll make a lot of them very difficult to exploit, but they're a safety net. So, try and keep that in mind. It's better to assume that all vulnerabilities could yield full code execution, but these things may, mitigations may temper how exploitable they are. And I think a lot of our approach from, mitigations and very tactical host intrusion prevention systems, we need to kind of take a step back. We need to look at how we actually run our applications and look at, instead of stopping a payload from running get proc address and load library, which is like the stupidest mitigation or defense ever. Basically, we need to look at privilege reduction. We need to look at what are the minimum rights that the application needs to run with, and a sandbox to basically ensure that these applications stay in there. You can imagine like a system where the application comes with a signed manifest saying, these are all the files that I'm going to read. And basically you can kind of enforce that at runtime. Virtualization, most Intel processors and AMD processors now support AMD or hardware virtualization. Besides using that for operating systems, what about using it for applications? There's a variety of things that you can do to try and just take the attack surface, to kind of contain an attacker. And the philosophy that I use is, if attackers could have created the data, they are running code. And that's the way you need to think of it. Because otherwise, we're basically just kind of taking one step back, and then the attackers, the defense is losing. And it's like, just kind of take a bigger step back to a defendable line and defend that line, rather than taking one step back, this piecemeal thing that has obviously not been working. So yeah, that's a little preview of my soapbox. Stop defending against tactics and start defending against strategies. Code injection through memory corruption is only a tactic. It is not the only way to exploit a memory corruption vulnerability. And even memory corruption is still just another tactic to make the application misbehave. If you look at how malware persists itself, how it spreads, these are all tactics, and we're not thinking about strategies enough. An attacker causing an application, a host, or a human to misbehave is an attacker's strategy. We need to start looking at things like that, rather than these very specific tactics. And if you look at how we treat, like how we identify things like H1N1, we didn't know what to look for. We weren't analyzing everybody person by person and looking for flu-like cells inside them. We found all these people with very high fevers. Some of them just keeled over and died. And we didn't know what it was, and we figured it out. We put out a vaccination. When a person is sick, it's very obvious. But when a host or an application is sick or misbehaving, we don't really know unless it's misbehaving in exactly the same way as one did a few weeks ago. And I'll use a metaphor that actually Dan Guido came up with on the bus up here. It's like going to school and your kid has the vaccination records, and he's meanwhile yakking on your feet. And you're like, oh, looks healthy to me, because he got his vaccinations a week ago. Even though he's feverish and yakking on your shoes, you think he's healthy. And that's basically how we treat systems. So we need to kind of stop doing that. Otherwise, we run the risk of dealing with the volcanic ash cloud from a cyber Pompeii or a cyber Yekdevil. Yeah, so look. Yeah. Do we want that to happen to the internet? I don't think so. If anyone has any questions. Yes, sir. I can take questions privately too. You can. Why don't you ping me afterwards? Any other? Yes.
Yeah. So the boss was talking about Pittsburgh and some of the techniques that was used with return programming.
So the question is about JIT spray, and those don't typically use return-oriented programming, because what a JIT spray lets you do is inject kind of code into an executable page. Like the JIT will, allocate new executable pages, and then if you can influence it, yeah. I mean, it'd be nice if you could do like return-oriented JIT spray, like what you might be able to do. If you can spray it, like instead of spraying bytes that you can influence, you can say, well, I can just put these in there, and those will be rets. It does break the KISS rule. A lot of things break the KISS rule for BISC, but I'm lazy, so once that gets fixed, then I'll make BISC stronger. Make it a biscuit. Yes. Yeah.
active access features and mine and all that. So you can potentially just pick one that has the type of quality of DSLR along the lines when you have one. There seems a pretty high chance that you'll have something there that's not built to the right and file off and something there.
That's correct. Yeah, the point was in a browser where you can dynamically cause it to load various modules, both in the operating system and third-party modules. If any of those are not compiled with the full mitigations, that, like, for instance, not ASLR, that may open up your browser to these attacks or to these exploits. Still, you need a vulnerability, but that may enable the exploitation. All right, it looks like it's 4:20, so I'm out of time. All right, if there are any other questions, just ping me offline or email me. I'm on the internets.